Welcome back to Topic 3 on Power Series in AP Calculus BC. This is actually your last video for the first semester. We're finishing with our second of two error bounds that we learned for this year. As a reminder, the first error bound we learned was actually last unit for our infinite series. It was the alternating series error bound. Today we're going to learn a similar error bound, but one that's particularly relates to all of our Taylor series that we're doing, and this is known as the LaGrange Error Bound. So we have a nice opener for you. Your goal is to write the fifth degree Maclaurin series for sine of x, and then compare the values of your fifth degree versus actually sine of 0. And then compare these guys and these guys. Decide on the radius of convergence, and then answer question 6. So go ahead, give those a shot, and we'll come back together once you're done. Alright, hopefully everything went well. Remembering that our fifth degree for sine is an odd function, so it looks like this. We always alternate in sine with both sine and cosine. Sorry for the bell, I'm recording at school. So I think there's my fifth degree. Okay. Hopefully you can see as well that if you substitute in 0, whenever you substitute in the center of your series, you should always get the same answer as the original series. In this case, 0, because sine of 0 is of course 0. However, when you start to compare p sub 5 of 2, right, and that's going to be 2 minus 2 cubed over 3 factorial plus 2 to the 5th over 5 factorial, and you compare that to f of 2, which is sine of 2, it's my guess that you probably won't get the same answer. But I'm going to set each of these up, and then we can go ahead and compare with the calculator and see how we do. It's 4 minus 4 cubed over 3 factorial plus 4 to the 5th. And then f of 4 is sine of 4, which is, of course, something. And so let's see what we can do. Let's see if I can remember this. I have my calculator somewhat ready to go here. So we had 2 first, I think. So it was 2 minus the fraction that had 2 cubed, which I think is 8, over 3 factorial, which is 6. Okay, and then it was plus 2 to the 5th over, probably should have done a fraction. Oops, I'll do that right now. 2 to the 5th over 5 factorial, and don't forget your factorial button if you didn't want to calculate that is not right there, it's the one with the exclamation mark. Escape, then an exclamation mark, there we go. Cool. And we end up with this guy, 14/15, or as a fraction, 0.933. Okay, I'm going to do p sub 5 of 4 right now because that should be a pretty easy replacement, I think. If I go up and copy this guy and then head over, if I go over one more, this one's going to be 4, right? And then 4 cubed, I happen to know, I think is 64. And then this has to be 4 out front. And then we want an approximation. There we go, 1.866. And then we'll do the same thing with sine. Sine of 2, sine of 4. Good, and also let's do the sine of 4. Good. 909, negative 756. All right. 5. What's the radius of convergence? Well, you could do the ratio test here, but it's going to be kind of silly because we should know the radius of convergence. Sine is continuous in both directions. There's no weird discontinuities. This radius of convergence is infinite. Right? And what that means then is that p of x, my polynomial, should look exactly like sine of x. They should be giving all the same answers. But how come if my radius is infinite, I'm not getting the same answers? In fact, I got the same answers at 0, and then 2 was pretty close, but honestly 4 was quite a decent ways away. How come my my tangent function, my power series, is getting worse for approximations? Well, and hopefully you would say that it's because we only used 3 terms here. the only way that p of x will give the same answers as f of x is if you put out an infinite number of terms at the end. If you write all of the terms, then the answers will be the same. I only wrote 3 of the terms. And so we can actually compare this down here too. I went ahead and showed you the graph of p sub 5 of x in red over here. And then I also showed you the graph of sine of x in blue. Currently, even though it doesn't look like it, they actually only intersect at one value. And the value that they intersect at is, of course, the center, which is x equals 0. Now, you can't really see it here, but what ends up happening is they don't intersect any further than that. The blue graph stays below, just barely below till here, and then crosses over at that one point and goes like this. So sine and its power series only intersect in one spot. Now what that means then is that for any value from like 1 to really 1.5, since you can't tell the difference, I bet the power series and sine will give almost exactly the same answer, right? Once we get to 2, they're kind of close, but 4, take a look at the difference here. This is the value that we found up above, right? This is my negative value down here, versus the value of my power series is way up here, right? That's that guy over here. And so we can tell that they are not super close together. Okay, so a way that we can discuss the proximity or the closeness of graphs to each other is through the error of the values of each graph. For example, if we look at the error values between p sub 5 of 4 and the actual graph at 4, we can see that the error is approximately, well, this is like 2 up here, and this is pretty close to 1 down here. That's pretty close to an error of 3. They're like 3 apart. What we really could do is we could subtract these two and see if they're actually 3 apart. Then they're not. Maybe they're 2.5, something like that. But I'll say it's approximately 3. Now, of course, if you did use our values, let's find the exact error. Might as well. I have them up here anyways. And remember, to find error of anything, you take the two values and you subtract them. That's going to tell us the difference between, and let's do sine of 4. And so the error is 2.623. Now, sometimes you might say, well, what happens if we subtracted them the other direction? Is the direction important? Well, here's this guy minus this one. Let's take a look at that answer. Oh, well, they're the exact same answer, just one is negative, one is positive. And that's why you might have learned, maybe in science especially, that when we calculate error, we always put the error in absolute value. And so we're going to conclude that right here. So the actual error is, I don't know, 2.6, I already forgot the rest, awkward, 2.623. Okay. Depending on which function is above the other, our errors might be negative or positive. And so to eliminate confusion, we always think of error as the distance, and distance is always positive. So our error function then, and in this case I'll write what we just found up above, the error of the 5th degree polynomial at an x value of 4, which is sometimes written as the remainder, we'll talk more about that in a second, of the 5th degree function evaluated at 4 is equal to the actual value of 4 minus our 5th degree function at 4. Of course, because this is an absolute value, you could write it the other way too. You could say our power series evaluated at 4 minus the function evaluated at 4. And these two values here, doing this versus this, are what came up with that guy. Now we generalized it using x and saying we could have an error function, which is just find any value of x, plug it into each of these, and that will find the error at that value of x. Okay. Error and remainder are used interchangeably when discussing the error of functions. A common use of the error function is when we want to see how accurate a certain number of terms is. However, we can't find the exact error with regards to how far off p of n is from the actual value, because that error is equal to all the terms that we didn't write. And that's kind of a confusing concept. So I'm going to show you right now. So we found p sub 5 of x, right? And that was x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. If I plug in a number here, like 4, that's what we did up above, then this of course is not equal to sine of x. Why is it not equal? It's not equal because I didn't write enough terms. The amount that I'm going to be off by is equal to all of the terms that I didn't write. So my error in this case will be minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial minus x to the 11th over 11 factorial, and so on and so forth. So this is a pretty concrete polynomial. There's 3 terms here, nothing bad. The error, though, is infinitely far. Eventually the error is an exact number. I mean, we got an exact number here and it wasn't exactly sine because it was off by this much. So if you can calculate sine, you could probably find the error if you wanted. But assuming that we don't have a calculator, it becomes much trickier. What we are going to do today is we're going to find a value for which the error will always be less than that value. This is known as a bound for my error, and the bound is the goal of LaGrange error bounding. Now we'll see some examples, so no stress. We first need to actually learn what the LaGrange error bound is, though. Now I mentioned before that this is very similar to the other error bound that we learned this semester, and that other error bound is known as the alternating series error bound. And as a reminder, what happens with that is when you're alternating terms, so if you had something like x minus x squared plus x cubed minus x to the 4th, so on and so forth, and that converges, then if you were to just use the first 4 terms here, the alternating series error bound says this sum is exactly equal to whatever your original function was, and it is at most wrong by just the next neglected equal to the next neglected or omitted term. So if I were to just use the first 4 terms, that answer is only off by the actual amount by a maximum of the next term that you left off. That's your alternating series error bound. However, not all power series are alternating. So our goal for today is to find a way to bound the error of any power series, to say, well, we added up these 4 terms, am I off by a lot? And you could say, ooh, by the Lagrange error bound, no, you're not. You're only off by a maximum of 2. And you're like, that's pretty good. Or you're only off by a maximum of 0.1. You're like, ooh, that's really good. But if they say, well, I don't know, you're off by a maximum of 100, that doesn't tell you as much, because you could be off by 100, but you could be off by less than that too. And we're going to talk about that right now. So here we go. If you take that our absolute value of remainder is equal to f of x minus p of x, then by using some algebra, then we can rewrite and say our equation is equal to the polynomial that you write plus the remainder plus all the terms that you don't write, and that should make sense. Okay? So we can write it out like so. We can say if our function is equal to the polynomial that we do write plus the remainder that we don't, and I should do 2 different colors here, the polynomial that we do write is, of course, our general Taylor polynomial, right? This is how we write a Taylor series, all the way up to here. But eventually, you as a human have to stop writing. And so let's say that I stop right here. Well, then how much am I wrong by? I am wrong by the remainder. And the remainder, although it's written this way, really means all the terms that we didn't write. How many terms are involved in that remainder? Well, if you stopped at the nth term, then the remainder has the next term and the term after that, and in fact it goes forever. So the remainder has an infinite number of terms. So you write a concrete number, everything you didn't write is what's left over here. How does that help us? Well, we're first going to learn about Taylor's theorem. Very intelligent man, Mr. Taylor. He is the same gentleman for whom Taylor series are named. And he's also known for his theorem called Taylor's theorem. Should probably write that out. Taylor's theorem has to do with the remainder of the series. And he was able to prove some very cool mathematics that if you use a power series to evaluate an x value, and I'm going to say, let's say we're plugging b in for x, that there is, and so let's maybe think about that first. So if I substitute B into a power series, a concrete power series where I only wrote a certain number of terms, then I would have to do all of this math. Okay, that's my concrete power series. And it's not going to be right because we only wrote a certain number of terms, and to have it be right we need an infinite number of terms. What Taylor was able to show is that if you look at the next neglected term, just like our alternating series, right? If you look at our next neglected term, there has to be some value that you can plug into just the very next single term, where this answer plus what you've already written will equal the exact value of the original function. And that is pretty darn powerful, realizing that wherever you stop, you would only have to add on one more thing to get the perfect answer. Well, that's really cool because now instead of the remainder being all of these terms, we can really say that the remainder is just the next neglected term. Now, there is an issue. And the issue is, cool, we know that the next neglected term will make our original power series add up exactly to the original function, but that is only with a very specific value plugged in, I should say, like that. I should say C as well, awkward. So what it's saying then is that we have our next term, and if you plug in the exact perfect value for x, you get exactly what's missing to make the original series equal to the original function. But the problem is, what do we plug in for x to make that happen? And the problem is, we don't know. So although Taylor was able to prove it, he did not give us a rule to say, we know we just need one more term, here's what you plug into the next term. We don't have that. So are we done? Is this useless? Well, no. So what we're going to do then is we're going to say, okay, we may not know exactly what this value C is that we're plugging in, but what Joseph Louis LaGrange, an Italian mathematician, was able to show is that although we can't maybe necessarily find the exact value, we can find the largest value. And so what we're going to do is think of this as still our general term in a Taylor series, nothing bad, right? Derivative over a factorial times the center. Okay? And what we're going to do is we're going to look at this in three parts, right? We can see we have the derivative, we can have the factorial, and we have, of course, the center. Okay? The factorial and the center are constant values. Right? There's no way that you can change these. This is just a power, this is just a factorial, they're concrete. The only thing that changes based on the different functions we use in terms of a Taylor series is the derivative. The derivative is different for pretty much every function. And so what we're going to do is we're going to say, well, if these guys are constant, they can't change. But I can change this. If we can find the largest value of C that makes this overall answer the biggest possible value, then we have now made this term as big as it can possibly go. And most of these terms won't be able to go infinitely large. So we've made this term as large as we can go. Then our remainder becomes the largest possible value, aka a maximum. So how do we write this? What are we trying to do? Well, we're saying that the remainder could be some exact value. But instead of it being the exact value, we're just going to find the biggest value it can be and then say, well, we might not be able to find the exact value, but we at least know what the exact value is less than. And we show that by taking this piece at the end, that's constant, it's going to be exactly the same, but the new piece is this max piece. So what is this max saying? It's saying you need to find the derivative. And then you need to figure out what's the largest answer you can get out of this derivative for some value C. Well, that's pretty vague because if you can plug in any number you want into the derivative, then won't it just be infinitely large? Well, in this case, no, because what LaGrange was able to prove is that you only need to find the maximum value of the derivative between 2 points, particularly between the center, so wherever you're centered, let's say you're centered at 0, then that would be 0, and the x value you are plugging in. So if we're centered at 0 and we're evaluating at 4 like we did on the opener, then we just need to find the largest value of c between 0 and 4, or we need to find the value of c between 0 and 4, which turns the derivative into the largest possible number. Oof, what do we need to memorize? Realistically, this. But not really, because this is just the Taylor series, which we've already memorized. This is still the Taylor series. We just need to really remember that this guy is the maximum, or is the value that makes the derivative the biggest between the center and the x value you're plugging in. So let's look at some examples. Given p of x, the Maclaurin series for f of x equals blah blah blah, what is the largest error that could result from using p sub 3 of x to approximate natural log of 2? Well, I think we could probably go through then and use our LaGrange Error Bound. The way we do it is we need to figure out first what degree did they use to approximate natural log of 2. And it looks to me like they used p sub 3 of x. So p sub 3 of x is just going to be out to the third degree, which is x minus x squared over 2 factorial plus 2x cubed divided by 3 factorial. And they used that to evaluate 2, right? So they wanted to approximate natural log of 2, so they're saying natural log of 2 is approximated by this power series over here. And be careful, because what did they plug in to create 2? It looks like they plugged in an x of 1. So we're saying natural log of 2 is going to be approximated by an x of 1. And so that's 1 minus 1 squared over 2 factorial plus 2 times 1 cubed over 3 factorial. If you wanted to simplify down, minus 1/2 plus 2/6, it's 1/3 I think. So simplifying a little bit further, let's make them all sixths. Why not? 6/6 minus 3/6 plus 2/6. 8 minus 3 is 5/6. So we are saying that we have the power series for natural log of 1 plus x. We are approximating natural log of 2 by replacing the x with 1. We're saying natural log of 2 is approximately 5/6. Their question is, what is the most you could be off by? So meaning, if you compared p sub 3 of 1 to natural log of 2, we said p sub 3 of 1 is 5/6. How much could you actually be off for whatever the actual amount of natural log of 2 is? Well, here's how we do it. If we used p sub 3 of x, then we need the 4th degree term in our Taylor polynomial. So, 4th degree. And the way we do that, degree with many e's. Okay, the way we do that is I would start by just setting up what the 4th degree looks like. It is the 4th derivative, okay, evaluated at, well, if we were creating this, this is a Maclaurin series, right? Evaluated at 0 over 0 factorial times x minus 0 to the 4th, right? That's our 4th degree term. Now, the Lagrange goes a little bit further, okay? So I'm going to move this 4th derivative out front and leave this blank for now. This should be a 4 factorial, not sure why I put a 0. And then it's being multiplied by something minus 0 to the 4th over 4 factorial. But when we were using this, didn't we evaluate it at 1? Right? So I think we replaced the x with 1. Now what about this derivative? This is where the Lagrange error bound comes in. And what it tells us is we need to find a value that gets plugged into the 4th derivative that makes this as large as possible. Okay, well, we're going to call this maybe C. You can use whatever letter you'd want, and we're trying to maximize this. So we want to maximize this by choosing C, and C is in between two numbers. It's in between the center, which is 0, and the value we plugged in, which is 1. So the question becomes, if you take all the values from 0 to 1, plug them into the fourth derivative of our function, what gives us the biggest value? And hopefully you're recognizing, oh wait, in order to figure that out, we probably need the fourth derivative of our function, drat. So original function, this guy. First derivative, that guy, which is of course 1 plus x to the negative first. Second derivative, negative 1 plus x to the negative second. Third derivative, 1 plus x to the negative third. Fourth derivative, finally, negative 6, 1 plus x to the negative fourth, or if you want, negative 6 divided by 1 plus x to the fourth. Okay, so let's adjust our LaGrange error bound here. We still have the max. We're saying c has to be something between 0 and 1, but we now have our derivative. The derivative is negative 6 over 1 plus, and we're evaluating this at c to the fourth, times, well, 1 to the fourth is 1, and 4 factorial, what is 4 factorial? 3 times 2 is 6 times 4 is 24. Technically, all of this should have been an absolute value as well. I was just being sloppy. Absolute value of that is just 1/24th, doesn't matter, so we're here. Cool. Well, just visualizing this, maybe we can see it. If you substitute 0 in here for c, you get 1 plus 0, which is 1. You get negative 6, which becomes 6. If you substitute 1 in here, 1 plus 1 is 2, right? Anything you add is going to make this bigger, and 2 to the fourth is 16. Negative 6 over 16 is a pretty small fraction. We're trying to maximize this, and hopefully you can see that the value that maximizes this is actually the one that makes the denominator the smallest, in this case, 0. So the maximum value here, using the absolute value, is going to be 6 over 1 plus 0 to the fourth, which is really just 6. And I have run out of room, which is awkward, sorry. So we're going to reduce this whole thing here to say the maximum error is 6 times 1/24th, which is 1/4. And that's pretty good. What they're telling us then is that 5, 6, excuse me, could be exactly natural log of 2, but even if it's not, the most that you are off by the natural log of 2 is by 1/4. So we have bounded our error, and we've said we found 5, 6, and we know we are at most 0.25 away from the actual value. Then, of course, the question in real life gets asked, are you satisfied with being off by at most 0.25? And someone might say, well, if we're dealing with trillions of dollars, sure, 25 cents isn't a big deal. But then someone else might say, well, I'm building a building in a really windy part, and if I'm off by 0.25 of a strength component and then it could fail, then no, I don't want to be off by that much. So it's very situationally dependent, but this is our LaGrange error bound. Now, I have good news for you. Lately, they have not made you actually analyze this derivative to determine which value makes it the largest. It's done much easier for you. So our next example is going to go much quicker, and I think you'll see what I mean. So here we go. The function f has derivatives of all orders of all real numbers. All orders means you can take the derivative forever. Values of f, its first 4 derivatives are given. The fourth derivative satisfies that for any x value, the answer to the fourth derivative has to be less than or equal to 48. For this x value, it's exactly 32, but for any x value, it has to be less than 48, as long as the x you're plugging in is larger than 2. Use the third degree Taylor polynomial for f about x equals 3 to approximate f of 2.5. Okay, let's build a Taylor polynomial. We'll just do one sentence at a time. We're doing this guy first, so let's begin. Let's see, third degree Taylor polynomial about x equals 3. Okay, so f of 3 over 0 factorial times x minus 3 to the 0th, right? 0th derivative, there's my trifecta, and there's my dual, so I'm looking okay, and we have the rest. Second derivative, derivative 1 factorial x minus 3 to the first. Second derivative 2 factorial x minus 3 to the second. And last but not least, third derivative of 3 over 3 factorial x minus 3 to the third. That looks like it's about x equals 3. Looks pretty good. So maybe we can call this p sub 3 of x. And we should also, I think, simplify this guy at least a little bit. So p sub 3 of x equals f of 3 is 6. 6 divided by 1 is 6. Anything to the 0th, we get 6 here. Cool. 6 plus. Next one. F prime of 3 is negative 10. No plus. Negative 10 over 1 is negative 10 times x minus 3 to the first. F double prime is 16. But 16 over 2 is 8. So it looks like this guy. And then f triple prime is negative. Didn't make that mistake again, but then I screwed up after. 24, this is 6. 24 divided by 6 is 4. And we're here. Nice. Okay, so we've got our third degree polynomial. What did they ask us to do? They asked us to use this to approximate f of 2.5. Okay? F of 2.5 will be approximated by our third degree polynomial evaluated at 2.5. So 6 minus 10 times 2.5 minus 3 plus 8, 2.5 minus 3 squared minus 4, 2.5 minus 3 cubed. Okay, cleaning this up. 6, and this part is optional, but that's okay, minus 10 times negative 1/2 plus 8, and that's negative 1/2 squared is going to be 1/4. And then at the end, minus 4, 1/2, that's going to be 1/8, negative 1/8 though, it looks like. Yes. All right, and then if we continue down, we're going to say f of 2.5 is approximated by 6 plus 5 plus 2 plus 1/2. So 11, 13, I'm getting 13.5. All right. We have approximated f of 2.5. Now we need to use the LaGrange Error Bound to show that the approximation differs by the actual value of f of 2.5 by no more than 1/8. All right, well, Taylor's theorem says that if we use the very next term that we haven't used, and the very next term that we haven't used, and you might have to write small here, but you'll survive. The very next term that we haven't used is the fourth derivative evaluated at something over 4 factorial times, what are we plugging in? 2.5. 2.5 minus 3 to the fourth. So Taylor's theorem says if you can find the exact perfect number to plug into the fourth derivative, then that is the exact amount that this answer is wrong by. But we don't have the ability to find that perfect number, so we say, I'm giving up on the perfect number, so instead we are just going to find the maximum, or the number that makes this derivative the largest possible. So we say C, and we say we're trying to maximize C, or use C to maximize the fourth derivative, where C is between the center and the value we plugged in. Well, we plugged in 2.5 and the center is 3, so C has to be between 2.5 and 3. This should all be an absolute value as well. As we work this out, right, the maximum that the fourth derivative can be, well, we know that. They told us the maximum the fourth derivative can be is 48, as long as we're using an x greater than 2. And we are looking at inputs greater than 2. So simplifying this, the fourth derivative's max can be 48. This is divided by 4 factorial times negative 1/2 to the fourth. Let's clean this up. 4 factorial, we said earlier, is 24. 48 by 24 is 2, and this becomes 1/16. So I think we get 1/8. Haha! Use the LaGrange Error Bound to show that the approximation differs from f of 2.5 by no more than 1/8. That is what this 1/8 means. This is the bound from the LaGrange Error Bound. It tells us that 13.5 could be the answer to f of 2.5, but if it's not, the most it's off by is 1/8. 2 to go. Multiple choice time. Let f be a function, derivatives, all orders, p sub 3 of x, third degree Taylor polynomial, Taylor power series, about f equals 0, converges, x equals 1. We know that the nth derivative has to be less than or equal to whatever n is, okay, divided by n plus 1. What's the smallest value of k for which the LaGrange Error Bound guarantees that these guys are less than that error? So notice this is the error right here. And they're saying, what is the value the error has to be less than or equal to? So this is the error bound. Well, they're using the third degree Taylor polynomial, which means that we're going to look at the fourth degree to bound the error, the next neglected term. So the fourth degree, so we're going to find the fourth degree evaluated at something over 4 factorial times, and it looks like they plugged in 1 for a Taylor series centered at 0. So 1 centered at 0 to the 4th power. What are we trying to maximize then? Well, we need the fourth derivative to be as large as possible, looking at an interval of c values from the center to what you plugged in. All right, well, how do we do that? Let's simplify things down a little bit. This should be absolute value again. So if we want to find the max of the fourth derivative at c, let's look at how to find the fourth derivative at c. And oh, they told us that any derivative we want has to be less than or equal to this. And that, I believe, is a maximum. They're telling this is the biggest our derivative could get. So if we're doing the fourth derivative at c, then we just use our formula with n being 4, and then our maximum is going to be 4 divided by 4 plus 1 times 1 over 4 factorial, and then 1 to the 4th. Cleaning this up a little bit more, everything's positive, we can drop the absolute value. I'm saying 4/5 times 1 over 4 factorial. Nothing too terrible. We just need to find a way to take that derivative and make it as big as possible. So last but not least, Taylor series, lovely. Fourth degree is used to approximate f of 1/2. What is the alternating series error bound? Oh, that's exciting. So if they use that fourth degree polynomial, let's just find the fourth degree polynomial and see what happens. So we do that by substituting in an n of 0. And actually, I'm going to rewrite this first. I think I like this a little bit better when this alternating factor is in the front, and then the rest of it I'll put the x to the 2n over 2n plus 1 factorial. Yeah, okay. So let's go ahead and try each of these. So for when n is 0, this becomes -1 to the first, which is negative. So we start with a negative here. 0, this becomes x to the 0th, and then 0 over 1 factorial. Cool. Plus, and then when n is 1, when n is 1, we get -1 squared, so that's positive. And then when n is 1, we get x squared over 2 plus 1 is 3 factorial. Next one is going to be a minus. I know we're alternating, and this is going to be when n is 2. When n is 2, we get a negative. We already saw that. This is going to be x to the 4th over 5 factorial. Now I've got the pattern. 1, 3, 5, 0, 2, 4. So I know that my next one, if I wanted another one for when n is 3, is going to be x to the 6th over 7 factorial, right? There's always one difference between the power and the factorial, and so on, so forth. Great. Now, if a fourth degree Taylor polynomial is used to approximate f of 1/2, well, a fourth degree Taylor polynomial is actually just the first 3 terms. It's up through n equals 2. So what's the next neglected term here? The next neglected term is n equals 3. And this is an alternating series. They asked us to use the alternating series error bound. The way the alternating series error bound says, or works, is it says, cool, you approximated f of 1/2 by replacing, and this should just be -1 right here, by replacing all the x's in this third degree polynomial with 1/2. Okay, and you get some sort of answer. The alternating series error bound says this is actually the exact answer for f of 1/2, maybe, but the most you can be off by is just the next term evaluated at that same, and error, so it's got to be in absolute value, at the same x value. So if we evaluate this guy, everything's positive, so I'm not worried. 2 times 2 is 4, third 2 is 8, fourth 2 is 16, fifth 2 is 32, sixth 2 is 64. So 1/64th, oh, they just left it. I should have looked down here. So this becomes 1 over 2 to the 6th times 1 over 7 factorial. And so with the alternating series error bound, it's very easy. You just take the next term, you evaluate it at whatever you evaluated the series at. This is the most that you can be off by. Alternating series error bound, very easy, just use the next term. LaGrange error bound, a little harder. Use the general format of a Taylor series, but maximize the derivative. So thank you for hanging out with me with power series. Our next couple days are going to be filled with review. And yeah, we have one test, we have your final, and you're done for the semester. So smooth sailing, and I'm excited to have you guys back next semester.